I thought about glossing over some of the dead ends that I ran down this week because there were more than a few, but it seems that people appreciate seeing the process, and I've been much more careful lately to take screenshots on the computer, also on the scope, having my camera handy to take clips and things like that. So, with my new ESD precautions in place, I was brimming with confidence as I changed out the 2022 decoder chip. But unfortunately, this confidence was to be short-lived as I fired it up, and lo and behold, the 514 number again. It wasn't there quite at the beginning, but after I reset it, it stayed there the entire time. With the possibility of the chip failure out of the way though, I was able to hone in pretty quickly on it, because I remembered that having a pin, I had shifted all these pins reading out of the chip down on the Arduino because I was running out of pins. So I remembered that when I had one in pin 0, it would give me an upload problem a lot of times, and I had to pull it out. I read that somewhere. And I realized that that second pin was on the TX pin, which you can see here. And I was serial outputting in order to read values out of it. So I thought, okay, this is pretty easy to test, right? If I shift it up 1, meaning that second pin will now be the first one, my error should go from 514 to 257. And that's what I got. So what do we do now? Well, we go to a bigger board that's more appropriately sized for this project and get rid of this problem forever. With that sorted out, it was fairly easy to make a little program that makes the motor follow the encoder. So every time the motor stops, it looks for the difference between encoder positions, which makes it look like it's just following it here. And this was also a good way to test the gearing ratios and other things that I've used to scale the inputs. Next up, we need different modes for this system so that we can have a record and a play mode. It's blinking red right now, which means that it's in nothing mode. That's both switches down, also both switches up, because that's not a valid position either. So what we're going to do here is click it up. It's in record mode now, which is the yellow LED on all the time. It gives us a given amount of time. I think it was 10 seconds in this case. Record with 10% of the time left. The red LED comes on to let you know to get back to your starting position. Now it's recorded. So we're going to flip that off. Now we're back in a neutral position, and we can enable the play switch whenever we need. So here we're going to do it with the motor attached. So we gave it a full spin clockwise and then a full spin counterclockwise. Wait till it's over. That was pretty good. It picked up the delay when I first started to rotate it, went all the way around, and the fact that it only went halfway back on the reverse was just a bug that I fixed later. That first test was pretty good, and it was at a 10 hertz sample rate. I was trying to see if I could avoid using an acceleration-deceleration function by just recording at a high enough frequency, so for this test we're at a 100 hertz sample rate. That was smoother, but I'm not sure if it's worth the extra data, because if I store 100 samples per second, each of them is an integer, for 60 seconds that's 6,000 integers for every axis. And I don't have an unlimited amount of storage on here, so we can start to run low. The other thing is that I can use interpolation between those points to smooth it out. Okay, so we're back at a 10 hertz sample rate, and we're going to use linear interpolation. This seems pretty simple, and it is, but you want to make sure that you get it right, because in this case I've recorded the position values, the changes in the encoder position, as integers, and so those are on the left with a lot of space in between them. And then we have our interpolated values on the far right side, and those are decimals. And then those get truncated back into integers because we need to feed integers into our time function to control the motor. So we have to add half to those because we're casting them back from floats to integers. And it's not that hard to get right, but it's something, you know, like for me getting started, if I don't pay attention, it's going to get screwed up. It's not a built-in function in my brain to think about that right off the bat. And then we bring the data in here, and I have the position, which is in blue, of the encoder, and you can see it going up, and then the derivative is in red. And this is all just making sure that my math is working correctly and that everything makes sense. With that very basic control strategy squared away, I wanted to do a load test on the motor, particularly since I built two separate things to do it. So on the bottom we have a roughly 1 pound coil of mag wire, or about 454 grams, and the radius on that wheel is about 1.5 inches, and we're just going to crank it up using our little program that we wrote earlier. And I had to put the torque settings at maximum in order to pull this off, because that's a decent amount of weight. You'll also see me hover my hand underneath because the holding torque was not nearly equal to the drive torque. It's time to move this extra encoder and motor over to the machine so that we can start doing a full workup test. But first I need to transfer these mounting screws onto the aluminum plate that we made, or the angle bracket. And what I'm going to do here is use some dye chem to paint on top of the screws, because I want them to line up pretty well. And if you just paint it on there a little bit, it'll stay wet, and then you can just lay this on top like that, and there you go. You've transferred the holes pretty well. You don't need transfer punches for something low precision like this. With the encoder mounted up, I made a small shelf for it to sit on along the axis of the bolt. It's a little bit ugly and a little bit off center, but it does the trick for now. This is why it's a prototype model and not a final one. I used a recommendation from the comments to attach the belt to the pulley there with just a screw, because it also makes it easy to get it on and off, in addition to the fact that I didn't have to order just a single extra pulley. For the time being, it's totally fine. When I go for more than 360 or more than 180 degree rotation, 90 each way, I'll need to upgrade that. And instead of using sorts of fancy couplers, what I realized too was that I could use shrink wrap, because shrink wrap works great, and I found one that was a pretty close size. Dropped that in there and got out the heat gun, blew some heat on it. Couldn't blow the heat accurately and do the camera at the same time. But we'll skip to it here, and you can see that it looks great. The machine's all together now. We give all the axes a dry run. Nothing seems like it's binding, so we're good to go. We transfer it inside and then begin doing some tests on one axis and then the other. I was very careful when I made that wood pulley that this upper arm is on, so that I made it just the right size, and I was able to use a straight 3-to-1 ratio for that, and it I can't tell any difference. The margin of error is within the flexing of the belt. The lower one is just a straight 12 to 1 ratio, and that one also, the error in that ratio is swamped by the play in the total system. The functionality of each arm individually was looking good. So this is authentic footage of the very first full workup test, I guess you could call it, of both arms together. So we're giving it some training motion here, and then we're going to fire it up. That was a pretty good test, and I was pleased at the time because it just worked, and you don't want to see it go in full throttle off into one side or the other, which is why I was sitting there on kneeling down. I was ready to hit the power button in short order in case things got out of hand. But you probably noticed it didn't go up as far as I had trained it, and it was doing some weird jerky motion when it was replaying. Much jerkier than it was when we were doing our tests with each motor individually. I went through quite a few different possibilities for things that could be causing this. One of the first ones, well, I've been keeping a list as I go along of things that I do which are not strictly in line with the recommendation. For example, the Megaboard recommends that you input between 7 and 12 volts. And I've been inputting 5 because I didn't have a 7 volt handy. My main supply is tied up with driving the motors at 24. So there were things like that. I thought maybe it's an undervoltage. I started going down this list of possibilities that could be wrong. And I went through quite a few. What I ended up settling on was that PWM signal was not correct that was coming out. I started to suspect that they were interfering, and I had an issue with that Timer 1. The Timer 1 library worked great on the Arduino Uno and wasn't working on the Mega. So I had switched to Timer 3 on this one, and this will be probably obvious to some people, but I was using Timer 3 for both of those. For both of those independent outputs, and I'm using the frequency control to control the motors. The way that I ultimately confirmed that the PWM frequency was the issue was by looking at the scope. I output them both channels into the scope and then stopped it so I could zoom in and look around. And you can see on the left here that we've got our blue signals, that's one. But then when we come into the other areas, there's a gap there, which is kind of weird. That shouldn't be there. And then when we zoom in on the blue and yellow areas where it started driving the second one, you'll notice that they're always tied together. And these are supposed to be both at 50% duty cycle and different frequencies. And you'll notice that the yellow one is the correct size for its frequency, but they're much too far apart. And what was happening here is, and so no matter where you look, you can see that the frequencies are tied together. I'm not quite sure why they were showing up as a wave here instead of a square wave, but I'm sure there's a reasonable explanation. The point is, they're all locked on the frequency together. And that's because I was outputting using the same timer, the first motor and then the second one, which is why the second one never jerked around and had an issue, because it spent the most time at the correct frequency. I spent quite a bit of time looking into this because there were several layers of things that I didn't understand. You start reading about clocks and you say, okay, that's very interesting. And then you look at how they shift the values, and they're using bit shifting to put the values in for the clock. And there's all these things, TC, CR, XB, and things like that, which are not that complicated. But if you don't understand it, it's easy to get confused. So I'd like to thank anybody who wrote anything about AVR timers in the past 10 years, because I probably read through your discussion. I had more bookmarks than I knew what to do with. And you can see that all the links except for the bottom one on the first page of Google are purple, and quite a few on other pages as well. I was able to confirm that I had it sorted out by putting both channels into the the scope again, and you can see here one of them is 1 hertz different than the other, and they're coming into phase and then out of phase. So there we go. We've got 2 different frequencies coming out. Problem solved. But the problem is not solved, because in having read through the timer 3, understanding how that works and reading other things, I realized that the pin maps were wrong on timer 1, which is why that library was not working on the Mega, although it had worked on the Uno. There's nothing wrong with it, it just wasn't mapped correctly because the timer 1 goes to different pins on the Mega. So I fixed that and I started using timer 1, and then I was getting these really weird spikes on different things. So you can see that here. I mean, just completely orders of magnitude higher than it should have been. And what I eventually settled on for this was that the timer 0 controls a lot of base functions like delay and milliseconds on the Uno, and I had assumed that was true for the Mega also, but I think timer 1 is also involved with the Mega, or with the base system functions on the Mega. So I just got rid of timer 1. I went to timer 4, and we got everything straightened out. That spiky graph was supposed to look more like this. The red one is the second arm, the smaller one, so that goes up. I should also point out these values are the absolute value, so the direction has already been stripped out of it by this point. So the small arm goes up, and it goes back down at about the same rate. Then the large one goes up, and then back down at about the same rate. Same rate as when it went up, I should say, which is why they're equal in height. Then we take both of them up and both of them down. This is what we want. Nice and smooth. It doesn't seem that hard, but by the time you grind through all the details and learn how everything works, it ended up taking quite a bit of time. But now that I've done it, you understand what's going on, and having learned it the somewhat hard way, you will rarely forget it. So this is why I find it useful to grind through the details at least once, because you just understand how it works. And I've found in other pursuits that long term that will cause less problems. Now that the thing is working and it looks good and I've verified that everything is as we want it, it's time to start thinking about some improvements on the control system. So right now it's only recording the rates and then playing them back. That thing has no idea where it actually is. The encoders are not doing anything on the replay phase. So that could be a very important advantage, because you can play back exactly where the position is when you have differing loads. If you haven't corrected in another way, you want to be able to do that. But that also requires a completely different control strategy. So that's something I'm going to be looking into next week. I want to add a filter, because there are some times where there are very small changes. It just gets bumped or whatever. That's why I'm holding it with one finger usually when it's done recording, because any little movement it records. So if there's a one-step movement that's surrounded by nothing, we should probably filter that out. That's not something that we want. And we want to think about smoothing out the motion too, but that can get a little bit complicated. So we got plenty of things to think about for next week. Thank you for watching, and I hope you come back.